Good afternoon, SWANA. Thanks for being here with us today. We are the Green Gators, representing the University of Florida. I'm Ashley, and I'm here with Vivian, Diego, Cassie, and Sam. And for the past 3 months, we've been working as a plastic waste task force for the state of SWANA. We've been assigned by the governor to develop a 10-year plan to reduce plastic waste, diverting it from 2 existing landfills. So today we'll be sharing our plan, which will be backed by an $8 million budget to encourage our selection of social programs and policies. We will also be selecting a new waste disposal technology, with mechanical and chemical recycling companies offering to open a facility for half of our budget, and we've seen potential in augmenting the current system in an existing waste-to-energy facility. Now, keep in mind these choices have been catered to United States political and social climate, with technological feasibility based on existing infrastructure in our country or in our state, Florida, where more details were available. So with proposed infrastructure and existing infrastructure, there will be a limitation on capacity. So the first part of our plan will be reducing the size of the plastic waste stream and improving the quality of the recyclables that we do collect to best take advantage of the capacity that we do have. So for this, we will be seeking to adjust consumer and company behavior through social policies and programs. So the best way to reduce contamination is to reduce it at the source. For this, we will be implementing infrastructural changes such as the switch to dual stream bins in residential areas, and we will be implementing increased bins and signage in public areas. While we will be making these changes, it will be even more important to implement educational initiatives. This is especially important for rural and low-income areas where they have very low recycling rates and very high contamination rates. For these initiatives, we propose hosting infrastructural seminars at government facilities and workshops at local businesses to encourage open discussion of waste disposal and educate the residents. We will also be proposing community events such as park and public cleanups, garden initiatives, and school outreach to encourage a greener mindset. We'll also be implementing a door-to-door feedback system, giving residents the opportunity to identify misunderstandings about recycling and improve disposal habits. Now, even if their disposal habits were perfect, the amount of plastic is overwhelming. At 650,000 tons produced per year, the only option that can handle this amount at our budget is landfilling. So to truly make an impact on the waste stream, we must reduce consumption, especially of single-use plastics. LDPE, for example, commonly used in films and bags, makes up nearly half of the plastic waste stream. So we will be proposing plastic bag bans with taxed paper bags to replace them, encouraging the optimal alternative of reusable bags. We also propose taxing food and beverage containment to discourage overconsumption and encourage companies to reduce packaging. So with the waste we cannot eliminate, we have the option of recycling. While we'll be shortly delving into the nuances between our recycling choices, we will be producing a recycled plastic product. In order for this to be a more circular resource cycle, we must actually use this product. For this, we propose a minimum resin content at 15%. To offset financial arguments, especially by Sugar Fizz, a nationwide brand partnered with a local plastic manufacturer, we propose tax credits for exceeding the minimum, and we propose selling the post-consumer resin at a discounted price for the transition. So, with a refined waste stream, we can now delve into our technology choice. To start us off, Sam, will you tell us more about chemical recycling?
Of course, thank you, Ashley. Now I'll go into our first scenario where SWANA accepts the $4 million offer from the chemical recycling facility. The key decision which had to be made for this scenario was the technology our chemical recycling company should implement at their facility. To determine this, we focused on the level of development of the technology within the United States, the types of plastic the technology could process, and the end product this process produced, among other things. After months of research looking at the various chemical recycling technologies, we decided to focus on pyrolysis, gasification, solvolysis, and hydrothermal processing. Pyrolysis and gasification are thermal cracking processes, with pyrolysis making a liquid product while gasification makes a gas product. Both of these processes are energy intensive and can deal with the majority of the plastic types. Gasification can better handle contamination but produces a lower value product, while pyrolysis requires more pre-sorting but is the most developed method. Solvolysis and hydrothermal processing are chemical treatment processes that break down plastic into its monomers through a combination of solvents and heat. Solvolysis can depolymerize plastic using less energy, but can only handle PET plastic, which makes up a small portion of the plastic waste stream. Hydrothermal processing can deal with high levels of contamination and high moisture contents, but hasn't been commercially applied in the US. In the end, we decided on pyrolysis since it's the most well-developed method and it can produce a plastic feedstock from LDPE, the largest percentage of SWANA's plastic waste stream, which can be sold as sugar fizz for tax credit. Now, to give you a brief summary of the pyrolysis process, the plastic is first pre-sorted, dried, and ground up. Once the feedstock is ready to be fed into the pyrolysis reactor, the plastic is heated and oxygen is removed. As the gas exits the chamber, it is condensed into a liquid oil product. This liquid pyrolysis oil is then treated further through a purification process to remove impurities before being fed into a steam cracker plant to produce ethylene, which can then be used as a feedstock for the manufacturing of virgin plastics. Looking at the facility requirements, hand-picking lines paired with additional conveyor belts will be added to MRFs since LDPE plastic has a tendency to clog sorting equipment such as screens. For the pyrolysis facility, based on the current state of operations in the United States, we estimated that it should be able to process around 20,000 tons of LDPE plastic per year. Within the facility, a reactor, condenser, purification plant, and steam cracker plant are the key equipment needed to process the plastic. A catalyst will also be needed to prevent wax formation when heating the plastic in the reactor. Now that we've gone through what will be needed at each facility, let's go through policies along with ethical, social, and environmental concerns with the pyrolysis process. The main policy that would be implemented in this scenario is unit-based pricing, where houses are charged according to the weight or volume of municipal solid waste in their bin, rather than paying a flat fee. This policy would allow households to save money by sorting recyclables into a separate bin, encouraging the new dual-stream system and recycling of plastics. Other general policies that Ashley mentioned will also be incorporated. Key ethical, social, and environmental concerns revolve around the location of the chemical recycling facility. The ideal location we decided on for the facility was Daunton. The existing waste-to-energy facility in Bumpa and existing concerns from Bumpa residents make it difficult to build in Bumpa without further pushback. Majora Beach is a coastal city, which would make it tricky to locate there without affecting tourism, and there are higher risks with storm damage. While waste management facilities such as chemical recycling facilities are typically built around rural areas, environmental justice concerns related to disproportionate impacts on lower-income communities pushed us to choose Daunton as the ideal facility location. Environmentally, pyrolysis is an energy-intensive process requiring high temperatures and producing gaseous products such as carbon dioxide and hydrogen chloride. In addition, the use of a catalyst creates an additional waste product, as a spent catalyst will need to be properly disposed of. While the products of pyrolysis can be optimized for high liquid yields and low gas yields, this process is still highly energy intensive, and the production of aromatic compounds brings about environmental risks with degradation of surrounding soil, air, and water if the facility isn't properly managed. Looking at the cost analysis for our first scenario, a majority of costs would come from the chemical recycling facility, with them taking $4 million out of our $8 million budget. After researching facilities throughout the United States, we found that costs far exceeded the $4 million the facility is asking for, ranging from tens to hundreds of millions of dollars in costs. While the pyrolysis oil can be sold as sugar fizz to make up for the high capital costs, we calculated that it would take approximately 14 years to cover a realistic facility cost of $47 million. For additional MRF equipment, we estimated costs of $600,000 and $1.45 million to support the first-year operations with the additional MRF equipment. We estimated a $600,000 cost for lobbying for the unit-based pricing policy, along with the lobbying of general policies. We estimated a $900,000 cost towards community engagement, with the first-year employment of 20 representatives covered, adding up to a total cost of $7.55 million, which allows for some cushion in case our calculated costs are exceeded. Now, Cassie is going to go into our second scenario.
Thank you, Sam. I'm going to be discussing our second scenario, which is our mechanical recycling scenario, in which we recommend that SWANA accept the $4 million bid from the competing mechanical recycling facility, request pelletization technology, and implement coordinating policy changes. Our decision-making process for this scenario was dependent on the accessibility of this technology, the feasibility of commercially operating a mechanical recycling facility, as well as the compatibility of our target plastics with this chosen technology. Mechanical recycling is well researched and widely commercialized in the U.S. And our target plastics for this scenario are PET and HDPE, both of which are general mechanical recycling target plastics. They comprise about 20% of SWANA's plastic waste stream, which, while not as significant as the LDPE proportion, is still enough to make an impact. Our material recovery facilities will be re-outfitted with ballistic separators in order to reduce contamination to our target 10%, as well as to separate PET and HDPE. Mechanical recycling can be separated into primary and secondary recycling. Secondary recycling begins with debaling, in which the PET and HDPE are broken out of the bales that they are placed in during material recovery. They are then placed in a shredder, which is pretty self-explanatory. It shreds the PET and HDPE, which are at this point separate, into smaller pieces for ease of pelletization, which leads me into our third step, pelletization. This third step could have also been extrusion technology. We chose pelletization technology due to the fact that we want a PCR product that we can sell to Sugar Fizz. As a result, we are requesting underwater pelletizers. This leads me into our fourth step, which is selling our product. Our PET pelletization product will be sold to Sugar Fizz at a discounted price, and our pelletized HDPE will be held in reserve for a possible extrusion extension of our facility, which will contribute to replacement recycling bins as part of our dual collection initiative. The environmental impact of a mechanical recycling facility will be primarily in emission difference. There's about a 20,000 metric tons of CO2 per ton of waste difference between recycling PET and HDPE as opposed to landfilling it. So a pretty significant positive environmental impact. In terms of social impact, we anticipate some health and lifestyle changes for the citizens of SWANA. We anticipate that single-use plastic use will reduce, and we anticipate the encouragement of additional environmental programs. In terms of policy for this specific scenario, we plan on focusing on deposit return schemes in which a consumer will pay an additional tax on PET bottles that they purchase, and then if they return those bottles, they will be reimbursed. This will increase the overall recycling rate. In terms of location, we plan to recommend that the mechanical recycling facility be located in the northern rural area of SWANA. This is due to the fact that it is in close proximity to all three metropolitan areas, thus reducing transport and transfer costs. A brief cost analysis of this second scenario indicates that the $4 million bid is relatively accurate to the technologies that we are recommending that SWANA request. Upgrading the 3 MRFs with ballistic separators will cost $1.4 million, in addition to a $400,000 cost for the deposit return schemes. Our policy and community costs are the same as scenario 1, resulting in a final cost of $7.3 million. This is a very economically feasible scenario, and this will be taken into account in our final decision and recommendation. Now I'm going to pass it off to Vivian, who's going to describe scenario 3.
Thank you, Cassie. In the case that SWANA rejects both Scenario 1 and 2, Scenario 3 will focus on retrofitting the existing waste-to-energy facility, selling the resulting products, and implementing policy changes. To explore the feasibility of this scenario, we visited Palm Beach County's Solid Waste Authority's Renewable Energy Facility. This visit played a major role in our decision-making process, which includes the types of plastics processed, the air pollution control technology at the waste-to-energy facility, and what to do with the end products from incineration. Before we start with the facility requirements, we must mention that the waste-to-energy facility has a capacity of about 130,000 tons. We based our calculations off the assumption that the waste-to-energy facility has a max capacity of 150,000 tons. Because a typical waste-to-energy facility can't handle more than 20% of their waste stream being plastics due to the BTU heating value being too high, this scenario can divert about 30,000 tons of plastic waste. Starting with the material recovery facility requirements, this scenario will require adding additional conveyor belts for hand-picking lines to separate out PVS and polystyrene. We made the decision due to the fact that incinerating PVC will release dioxins and incinerating polystyrene results in the highest GHG emissions, as seen in our WARM evaluations. WARM evaluations also showed that incinerating has higher emissions than landfilling. To help mitigate the environmental impact and address the health concerns from the citizens of Bumpa, we proposed retrofitting the air pollution control technology at the existing waste-to-energy facility. In the January 23, 2024 Federal Register notice, The EPA proposes more stringent emissions limits for municipal waste combustors. Because we plan to increase the percentage of plastics being diverted to the waste-to-energy facility, we will mainly focus on reducing the pollutants being increased by the plastic increase, which are hydrochloric acid and sulfur dioxide. In the same Federal Register notice, Table 8 estimates compliance costs for all the existing waste-to-energy facilities in the U.S. to add the necessary controls to meet the proposed standards. Since we are focusing on acid gases, the total annual compliance cost is estimated at $12.9 million for the 75 existing waste-to-energy facilities in the U.S., making the compliance cost for one facility $172,000. We calculated the revenue of this scenario could produce from electricity production and recycling bottom ash as an aggregate for concrete. These values were based off the numbers given to us by Palm Beach County Solid Waste Authority. At 575 kilowatts of electricity produced per ton of waste, our waste-to-energy produces 86 million kilowatts. Sold at $60 per megawatt, this generates a revenue of about $5.2 million. However, according to Palm Beach County Solid Waste Authority, a majority of the operating costs will be offset by the revenue produced from electricity. One of the main products of incineration is bottom ash and fly ash. Recycling bottom ash as a concrete aggregate will help offset some of the environmental impacts from incineration and will make use of a product that would otherwise be sitting in a landfill. Our waste-to-energy produces 15,000 tons of ash, which can be recycled into 6,000 tons of concrete aggregate. Sold at $30 per ton, this generates a revenue of $180,000. Policies will be the same as Scenario 1 and 2, mainly focusing on the single-use plastic ban, which is explained by Ashley. Programs differ slightly as the dual stream collection system will be to help sort out PVC and polystyrene. Community outreach will target health and environmental concerns of the waste-to-energy facility by educating the public about air pollution control technologies in place. Recycling education in schools is based off of Palm Beach County Solid Waste Authority's education program, which includes taking students on field trips to the waste-to-energy facility and visiting classrooms to educate students on recycling. Breaking down the cost analysis, the cost for retrofitting the air pollution control at waste-to-energy is $172,000, as explained earlier. Additional conveyor belts for hand-picking lines and covering the wages for additional employees for the first year are the same cost as Scenario 1, which was explained by Sam. The cost for 1 year of policy lobbying and 1 year of employment for 20 representatives are also the same as Scenarios 1 and 2. The education programs for schools is $2.5 million for 5 years, with the remaining budget left to cover additional years if the education programs prove to be effective. This totals to about $6.2 million, which fits nicely within our budget of $8 million. Now Diego will be talking about the recommendations based on the analyses of all three scenarios.
Thank you, Vivian, and the rest of my team for going over all three scenarios. Now it's my turn to talk about the recommendations and the conclusion of our findings. Now, as you can see from this table displayed, the investment costs in main facilities are shown. If you look towards the end at the capacity section, you see that mechanical and chemical recycling have the same plastic capacity of 20,000 tons a year. Now, if you look at the augmented current system, is 150,000 tons a year overall capacity. Although for plastic capacity, it's only about 20%, being 30,000 tons a year. Now, if we want to take a look at the economic benefit, we can fully eliminate chemical recycling, as the probability of having a successful recycling facility for chemical recycling is extremely low with the offered cost we have. As you can see, our offered cost is $4 million, while the realistic cost of this facility is greater than $50 million. Now, if we then look at the augmented current system, we see that the offered cost and the realistic cost is roughly the same, although the environmental impact is in the negatives, while the mechanical environmental impact is positive. So this takes us to the product revenue for each of the scenarios. Now, you can see that the yearly revenue for mechanical recycling is a lot higher than the rest, being $3.6 million, while the lowest is augmenting our current system at $180,000. I would also like to mention that the social and policy impact for each scenario is similar, although there is a little bit of differences in the specifics, since as you can see, the target plastic for each of the scenarios is different. Now, with all this being said, we recommend that mechanical recycling is the best option for the state of SWANA, and you may ask yourself why. This is because it has the best economic incentive while also having the lowest environmental impact. Overall, it also has a multitude of social benefits, including job creation through our recycling feedback initiative, as well as environmental and recycling education, and overall it progresses our society to a more environmentally conscious public. At this time, we would also like to thank the SWANA judges for being part of our today's presentation and everyone that has helped us throughout our research. Thank you.